Hi everyone, my name is Corey and I am one of Drayton Hall's archaeologists. And while I've been sheltering in place, I've been working on an ongoing project studying added timber in Colonoware. For anyone who doesn't know, Colonoware is a low-fired earthenware made locally by enslaved Africans, their descendants, and Native Americans beginning in the colonial period. One of the best ways to understand the person behind a ceramic vessel is to look at the steps that a potter would have taken to produce that object. One of the choices that would have been made is how much temper to add to raw clay. Raw clay cannot be immediately used in pottery making. It has to be essentially cleaned and then mixed with other materials to make it hold together, kind of like eggs in baking. These added materials are called the temper. There are many different types of temper, from quartz sand to mica, shell, grog, which is broken pieces of old pottery that are added to new pottery, and their presence in a ceramic marks an intentional choice by the potter. Colonoware is tempered with quartz sand mostly, although sometimes you see other additions like mica, grog, or limestone. When cataloging Colonoware, we capture this attribute, not only the type of temper used, but we also want to know how much was added. This is a little more difficult to determine for two reasons. So here you can see two sherd profiles, or the broken edge of the sherd, and this is where we look to analyze the temper. So quantifying how much temper was added is difficult because one, a broken or bumpy edge is not easy to analyze no matter how much you clean it, and two, determining a percentage has really only been done visually. And although catalogers become relatively skilled at this over time, it is still a fairly subjective process and one that varies between catalogers. Looking at sherds under a microscope, as shown in this image here, gives a clearer view of added temper, but it still does not help with quantifying how much temper that potter added. So to combat these issues, I've been participating in a temper analysis study that aims to develop methods that not only calculate the temper density, but that are also minimally destructive and easily replicable. So this study has been spearheaded by my colleague, John Marcoux, who you can see here, and he has developed a workflow that will allow us to quantify this attribute. And so he, I, and another colleague, Jeff, who you can see here, have been pulling samples of colonoware from several different 17th and 18th century sites to essentially test how accurate this process is and if it will give us reliable data. So I'll show you how it all works. So the first thing we have to do is obtain a completely flat profile, not the jagged broken edge we always see from a ceramic sherd when it is excavated. Yes, this is destructive to the sherd. Archaeology as a discipline is destructive, meaning once we excavate a site, that exact process can never be redone. The site is forever changed. That said, we employ many methods to mitigate the amount of destruction done, and in lab analysis, we do the same thing. This particular project is mitigating the level of destruction in two ways. One, instead of essentially cutting off a chunk of the sherd, which is sometimes done in ceramic analysis, we use a Dremel to simply grind down a flat edge. This way, we lose as little of the original sherd as possible. And two, we are only performing this analysis on a sample of sherds, and therefore we are not changing all of the assemblage. One of the long-term goals of this project is to provide a study collection and image database for assemblages that cannot be similarly ground down for whatever reason, and so they can use our study as a comparison. In the long run, hopefully this study will actually decrease the level of destruction needed for ceramic analysis. So the second step to the process is to scan the now flat profile using a very high-res scanner at 6400 dpi. This ensures a high-quality image that most accurately captures the exposed temper. Then we bring this image into Photoshop using the scale to tell the program the true size of our image, and we'll crop the photo to make sure we are only analyzing the profile itself. I have several macros set up on my Photoshop, so you won't see me go through each individual step here, but we essentially use 3 different levels of image adjustments to edit the image. The goal is to obtain the highest amount of contrast possible between the clay and the quartz sand inclusions, which should stick out as white, like you can see here. Then using the threshold tool, Photoshop will make the image dichromatic. The clay should turn black and all visible temper should turn white. This is the only slightly subjective step in our process. If the profile has a very high contrast like this image, I do not have to change the threshold amount at all. I just check to make sure that all visible inclusions are made into little white blobs. Once I've confirmed this, I can save all these images. So many files produced here to cover all of these steps, and then I'll capture my measurements. First thing I want to measure is the entire profile, and this is why setting the scale at the beginning is so important. And Photoshop will measure the shape and produce the result at the bottom of the screen. So there it is. So now I know that the total area of my profile is approximately 133 millimeters. Then using a special color selecting tool, I tell Photoshop to select all white shapes. And so this will capture all temper shapes and it will measure each individually. Not only does this capture the area of each shape, but also its dimensions. And then I will, of course, export this data. And we will use this data in the next few steps. All right. Next, I want to manipulate this data a little bit in Excel. First, I need to create a maximum dimension column and then record the total area of temper. And we'll use this data in the next step. So next, I will use a program called JASP. This is a free program that will calculate some statistics for the temper measured on this sherd, providing me with the average maximum measurements and the corresponding standard deviation. I will also transfer my data on the calculated density from this program. One of the things I am also doing in this step is filtering out all temper that measures less than 0.06 millimeters. This is the geological definition of silt, and the hypothesis here is that all clay will contain a certain level of naturally occurring materials, even if it was cleaned before the potter added intentional temper. So one of the things we have to remember is that we are looking at both naturally occurring and intentionally added sand. Therefore, I'll record data for all of the temper measured, as well as a data set representing only those larger than silt. This is something that my colleagues and I will play around with in the future, how to distinguish and filter out naturally occurring temper. For now, however, I've achieved a pretty good idea of how much temper was intentionally added by the potter. For this sherd, added quartz sand makes up somewhere between 9 and 9.5% of the clay. Not only is this an awesome calculation in and of itself because now I know how much temper was added, but we can also compare the temper densities across an assemblage. This is where we get into the really awesome and nerdy part of the study. My colleague John has been plotting some of the data as Jeff and I have finished with it, and he's begun to notice some clustering. So each one of these shapes that you can see here, whether it's an X, triangle, or square, represents one sherd. And John has plotted each sherd based on those statistics we recorded earlier. And right now we can see 3 groups forming, and this possibly reflects 3 distinct pottery making traditions, specifically when it comes to the amount of temper being added to the clay. We can also look at this data and how it differs between sites, or how it relates to the different surface treatments observed, or their thicknesses, or any other attributes. So as we obtain more data, I think we have just a few more final samples to finish up. We will begin to analyze these statistical trends and essentially what we can learn from studying this particular choice in pottery making. So I know this got very math and science heavy at the end, but the most important thing about this study is that it is getting at a decision made by the person who created a particular Colonoware vessel. Because we do not have historical records to help us research the manufacturing, use, or importance of this ceramic type and the people who interacted with it, we need to rely on these methods to essentially research the human behind the artifact. Like I said, this is an ongoing project and one that is testing out an entirely new method, so I will be sure to update everyone on new information as it comes. And I'll check back in soon on other research from my makeshift lab. Thanks for watching.